session on what's looming in Java, the why and what of Project Loom. So before we get started, my name is Venkat Subramaniam, and we are really in an exciting time with Project Loom just around the corner for us to be able to start using. I think that the journey is going to take a little longer than that as we go through and find that different tools and vendors and products are beginning to support it. But it's a good time for us to know what it is and get ready for it. Best time to ask questions or make comments is anytime you have a question or a comment. So please don't wait till the end. Anytime is a great time. I'll be delighted to hear your thoughts, your questions. So let's talk a little bit about what is Project Loom and what does it provide and how would we benefit from such a tool. That's what we want to focus on here today. The first, of course, we've had the ability to do multi-threading in Java from day one. We've had the multi-threading library as part of the Java ecosystem from the beginning, and we've all had opportunities to write multi-threaded code. But oftentimes, there are a few confusions we often end up with. And that is, the question is, what is parallel and what is concurrent? And we often, ask this question. So I'm going to make a silly analogy of what that really is. So here I am within the confines of this podium here to walk, and as I'm walking around, I'm also speaking, and that is parallelism. So I don't have to pause my walking to say words. I don't have to pause saying words to walk around, and most of us, can execute different tasks in parallel. We can speak, and at the same time, you could be listening to your music. Sometimes you keep watching TV. At the same time, you write code. Things that we do in parallel oftentimes. So parallelism is where different tasks continue to evolve at the same time, but at any given slice of instance, there are more than one thing you do at the same time. On the other hand, if I were to be speaking here and I'm also interested in drinking this coffee, it could be an hour where I might empty this coffee in the middle of this talk, during this talk. I'm going to say a few words in this talk. So if you ask me what do you do in this hour, I could say I spoke those words and I drank the coffee. But it is rather impolite, and if not, at least not healthy and safe to drink and speak at the same time. I won't try it. Well, I can only drink and speak concurrently. I cannot drink and speak in parallel. Maybe some people can, but I cannot. So that's kind of the distinction between parallel and concurrency is given a certain amount of time, both the activities progress both in concurrency and in parallel. But given a slice of time, a point in time, in the case of parallel, two things are running at the same time. In the case of concurrency, one or the other. We've all used programming with concurrency and parallel quite a bit, but now we talk about what about asynchronous programming? Well, asynchronous programming is a lot more important, I would say, or as important as parallelism. And unfortunately, in the world of Java, we haven't done as much in asynchrony as much as we did in parallel and concurrent. Now, I know it's a little hard to accept it, to say that JavaScript got it right, but sometimes it's okay to accept it. And JavaScript took the bold step and said, we're not going to do parallel, we're going to do asynchronous programming. And 25 years later, we look back and say, that was a good move, wasn't it? So what is asynchronous programming? Asynchronous programming, I want to put it in blunt words as what it means. It really means non-blocking. So non-blocking simply means you don't want to block and wait on something to finish before you go off to do other things, so you want it to be non-blocking. Now, the benefit of non-blocking is really your better use of your resources. So if you're going to perform a call to an external service, if you're going to block and wait on that response, that may not be really an efficient way to run the code. For example, we all can agree that one of the first rituals we have when we get to work in the morning is to fill up our a coffee cup or whatever beverage you are interested in. But you go to the coffee machine and you realize that it's empty. How horrible that is to find the coffee machine empty. But what do you normally do? You turn on the coffee pot and ask it to brew, but you don't get grumpy and stay there until it fills up for the next 15 minutes. You're going to say, I'm going to turn on the coffee pot, let it brew, while I'm going to go talk to colleagues and do other piece of work, and maybe I'll come back and get the coffee later on. Or one of your colleagues who's so kind enough says, hey, I know you're really interested in coffee, but you got to go to this meeting. You go over there, I'll swing by and give you the coffee along the way. And what a nice friend to have to help you with caffeine in the morning. So the point is, it's a non-blocking. You're not waiting for this to happen. That becomes efficient. But unfortunately, though, let's think about this a little bit about what we have been doing for the past several years, several decades, actually. Well, the good news is, when I first came across Java, I was really excited. And the reason is, I came from the background of programming in C++. In C++, your multithreading library was not the same across platform. Whether you programmed on Windows versus, on the other hand, on a Unix-like system, it was very different. Java, when it came out, said, write once, run anywhere. So here's a standard library for doing multithreading. Off you go, you can write the code, and you just can deploy it on different operating systems. And that was a breath of fresh air. It's like, wow, that's awesome. I can just deploy this. Not only that, some of you may have experienced the times of CGIs and systems we wrote where when a request comes in, you started an external process. Starting a process is expensive because a process has to come to life, execute, die away. And so we said, hey, we don't want to really create processes like that, at least back in time, and we wanted to really use threads. Well, the nice thing about threads were considered to be lightweight. Now, the term lightweight is very relative. I often say everything is relative, right? For example, you could say children are, much lightweight than us, the adults. But I'm sure sometimes when you lift up a child, you say, my gosh, you're getting heavy, right? But that's purely relative speaking. Doesn't mean the child is suddenly heavier than an adult, but the child is heavier than what the child was before. So essentially, the term heavy and lightweight and heavyweight is very relative. And the question I want to ask here is, how many threads should I create? Well, or how many threads can I create? Well, it's really important to ask this question in a very careful way. Asking the question, how many threads can I create, is like asking the question, how much food can I eat? Very dangerous question, because I can eat a lot of food. And people often misjudge me. They look at my size and determine the amount of food I can eat. I disappoint them actually in the wrong way. So I can eat a lot of food, but that's not healthy by any stretch of imagination. A better question to ask is, how many threads should I create? This reminds me of an experience I would never forget. I was working on a project with a really good colleague. We were pairing and working on it. They hired me as a consultant to help them improve the process and the performance of their application. And this was a big data project which required a lot of performance. And we took a sample because we wanted to see how we can really rework the code to improve performance. So we took a sample data. Now, in the sample data that we took, we ran the code sequentially. And when we ran the code sequentially, the code took 30 minutes to execute this sample. It's really a huge amount of complexity in terms of its power the application is doing. And so we ran it. It took 30 minutes to execute. And so we spent the time to rework the code to make it parallel. And I was so proud to show my colleague how beautifully we improved performance. And I showed that with that effort, we are running the code in 5 minutes now in parallel compared to 30 minutes. And he looked at the code and he said, that's interesting. I want you to increase the thread. I said, no, you don't want me to increase the thread. And he said, no, I want to increase the thread and I pay you for doing so. I'm like, okay, you are the boss. What can I do? So we increased the thread. And what took 30 minutes to run sequentially and what took 5 minutes to run in parallel now took 90 minutes to execute. And he said, what went wrong here? And I said, because you were greedy, you wanted more threads. The problem really is when you create more threads, you don't automatically get better performance. The problem here is when you create a number of threads more than a certain level, then your application is going to start crashing and context switching really is going to bring it down. So the question really is, how many threads can you really create? Or should you create? And the answer depends on First of all, as we know, on the amount of memory that you have. But unfortunately, though, that is not a good measure in some cases. This particular company that I was talking about, I love them because it was like Christmas every day working for them. Because I would ask a question, and almost all the answers they gave me followed with a question like this. I asked them one day, how much memory does this machine have? And their answer was, why? This machine has a main memory of 1 terabytes, but if you need something bigger, please let us know. I just love these people for the way they respond to it. And I asked them how many cores this machine have. And they said, oh, that one only has 1,000 cores, but if you need something bigger, please let me know. It was a government-funded project. Okay, it was great. So the point really is, it doesn't matter how much memory we had, there were other constraints we had to work with. So essentially, in this particular case, how many threads are we allowed to have? I'm going to say one of the things you want to really think about in terms of the number of threads is the following. I'm going to say number of threads that you are allowed to create or should create is less than or equal to, I'm going to say as a very first number, I'm going to say it's equal to, less than or equal to, if you will, a number of cores on the machine. So that's the very first thing you want to start is the number of cores on the machine. So if your tasks are computation intensive, you want to definitely make sure that the number of threads, if you will, so I'm going to say is threads is less than or equal to number of cores. You want to definitely abide by that. If you create more threads than that, what you're going to do is to lose on trashing because the CPU context switching is going to bring this down. On the other hand, if your tasks are I/O intensive, then what happens is you're going to go a little further than that. And that is to say that divided by 1 minus, if you will, the blocking factor. So the blocking factor is the amount of time a thread is going to spend being blocked and not use the CPU. So for example, you could say a blocking factor, if you will, is going to be a value which is 0 less than or equal to the blocking factor, which is less than 1. And that's basically the formula that you want to think about when it comes to how many threads you should be creating. So for example, if it's I/O intensive thread, you can say in this particular case, if the blocking factor, if you will, you can say if the blocking, let's say blocking factor is, and you can say if a blocking factor is, let's say 0.5, then you can go 2 times the number of cores because a 0.5, 1 minus 0.5 is 0.5, 0.5 in the denominator comes up as 2 in the numerator, so that works. If the blocking factor is 0.9, you can go actually up to 10 times the number of cores. But if you really think about it, the problem in this case is, this is a pretty sad story, isn't it, if you really think about it? Because what's happening here, if you have, let's say, 100 cores, let's say, if you have 100 cores and you have I/O intensive, you may want to go up to, let's say, 1,000 threads. So the number of threads is 1,000, you say. Now, if you really think about it realistically, 1,000 threads may be too many for some applications and too little for others. So if you really have an application where you want a lot more processing, what is your answer? What is your solution? You're going to say, gosh, I cannot put more on this machine. I have to scale horizontally. Now, to scale horizontally, you're going to become elastic. You deploy it on the cloud. And why are you doing all of that? Well, the reason you are doing all of that is when a thread is performing an I/O, you are saying you can switch over to perform another task, but fundamentally, the threads are not being very effective. Even the threads are not being effective, you are saying this is how many threads you can create, and now to really scale, you got to go horizontal, you got to become elastic, and the companies that are very happy with this news are the cloud service providers, right? They are like, keep going, what's holding you back? And keep sending us the check and we won't have a problem doing it. And elastic means their services expand, your bank account shrinks, right? So that's basically what elastic means. And that's not a good situation to be in. But if you really ask the question, why are we spending all this money? But not only that, there's another problem we have to deal with here. We are messing up the environment quite a bit by using more resources. But here's the question you really want to ask. When you deal with multi-threading, why are we dealing with multi-threading? Well, because when you have a thread of execution, if the thread performs a task that's going to take time, you're saying, look, the thread is not available, we are in trouble. So what do if the thread is going to get stuck? You're saying, I have an idea, create more threads. Now think of that logically. Does that really sound like a great idea? If something is not good, create more of it. How could that be a good decision in general? But then, of course, we all have done that over the years. Let's talk about this a little bit. Now, of course, multi-threading, you say, we all have written sequential code, isn't it? And of course, the question is, why not be happy with the sequential code and be happy with writing code sequentially? Well, the problem is, in the case of an existing programming model, the threads get tied to a task for most part. And what if a task is not going to go any place and it gets stuck? You say, we need to really create more threads. But here's the problem. Multi-threading comes at a huge cost, isn't it? Now, I'll give you an example of this to think about it. We all have worked on single-threaded applications. But if you ever think about it, I'll give you a clue. How do you know you're working on a sequential application? Here's a very simple way to know. When you go to work, people actually smile at each other. That's when you know you're working on a sequential application. They smile at each other, they are nice to each other, they go out to lunch together, and it feels like you're working with a nice group. And then everything goes on just fine for a few years, and one day somebody says, we really need to improve performance, let's bring in multi-threading. And what happened that day? That's the day they had the joy in the team for the last time, because everybody gets grumpy after that. And things don't work, there's locks everywhere, synchronization everywhere, the code becomes unmanageable, and you are spending way too much time debugging the code. And you are nostalgic, because you look at the code in front of you, it looks like a monster to you. And you think of the time when the code was beautiful, you could look at it and understand, and you're like, what happened to that code? I don't even recognize this code anymore, right? It looks like a monster in front of you. And as you're looking at this code and you're debugging late in the night and you're getting very frustrated and you tell yourselves, I've had it enough, and while you're fixing this bug, you apply for another job. That's called concurrency, isn't it? And you said, I'm done, I don't want to do this anymore. Well, that's kind of the problem we get into very quickly. But then ask the question, why did we go down this rabbit hole? Why did we really get to this particular situation? Well, that's because threads are not very efficient. So the question to ask here is, how can we convert this code in a way that threads are a little bit more efficient? What can we do about it? We'll come back to that question in just a few minutes, but let's think about this a little bit further in here, if you will. Let's not even worry about the course for a few minutes. We'll come back to that a little later, but let's take a little example here and try this. So I'm going to say int, let's say max equal to, let's say a value of 10. Let's start with a very modest value right now. And I'm going to say over here, let's say a thread, we'll say thread is equal to a null for now. Let's say for int I equal to 0, I less than max I plus plus. And I'm going to simply say over here, let's say thread equal to new thread. Let's go ahead and say new thread. And I'm going to say this is a sample. Do work is the method I want to call right now. And then I'm going to say start the thread over here for execution. And when you're done with all of that, I'm going to simply say thread.join. But before we do, we will go ahead and say, let's say started. Let's go ahead and print that out. And then we will simply output, let's say in this particular case, when we are done with it, we'll say done to say that we are done with it. So a reasonable piece of code, nothing really exciting. It's going to ask me to handle exceptions. And as experienced programmers, we know exactly how to take care of that. So we'll take care of that right there. So now what I'm going to do here is to say that I'm going to say public, let's say static void do work. And all I'm going to do in the do work method is we're going to simulate, let's say simulate some work. and maybe performing I/O, etc. So I'm going to simply say over here try a thread.sleep, let's say about a 5-second delay right there. And then we will simply say a catch exception, and we will put the exception right there and be done with it. So that's a little bit of code, 10 threads we are creating. That's all we are doing, so nothing really complicated. So you can see it started, it says it's done, so not a big deal. So we are able to see the output. But then I'm going to come to this code and say, hey, how about creating 100 threads, and I'm starting again 100 threads later. I'm going to stop it, not a big deal, right? So no worries at all. What if I go to 1,000 threads at this particular point, and you can see that 1,000 threads, my machine is saying I can hold it, not a problem. So that worked as well, no worries. What if I set a 5,000 threads on this particular machine, and you can see that in this particular case, it says, oh, you know what, 5,000, no worries, I can handle it. But what if I were to go to 10,000 threads at this particular point? If I say 10,000 threads though, you can see it's complaining. And it is saying out of memory error. It says unable to create native threads. It says possibly out of memory. It's not even sure, folks, why it really failed. So that's kind of the pain it goes through, as you can see right there, right? So as a result, it just couldn't take. So somewhere between 5,000 and 10,000, it failed. Let's kind of call it even 7,500 threads, it bailed out. So the question you want to ask is, do I really want to push it to 7,000 threads and be happy with it? But why? What am I doing really? And if you really think about it, all I was doing was sleeping, right? So I was not doing any real work, and yet I couldn't go beyond a certain number of threads. So the question is, what's going on? Well, the problem really is that when you have a task, and in the past what we did was, we tend to tie the task and the threads together. So when a task is blocking, the thread is blocking as well. And when the task is ready to move, the thread is able to move. So in this particular case, the function said sleep, or you could be doing an I/O, or you could be logging, you could be accessing a file, you could be using a remote service and get data from a remote service. It doesn't matter what you do. What does the thread say? The thread says, oh, I'm waiting for this to finish. And imagine this for a minute. Imagine you are visiting a really good restaurant. And in this restaurant, there's an amazing waiter who is known to be really efficient in service. And the waiter comes over and says, what do you like to drink? And you said, what are the options? And the waiter gives you a list of things you could have. And he or she says, what would you like? And you're like, I don't know, what am I in mood for today? And you're thinking, and what does a good waiter say? The waiter says, why don't you think about it? I'll be right back, and leaves your table and buses other tables, and after a while comes back to check on you. Or it could be possible that some other waiter comes on and says, hey, would you like to have some more water? It's not like that only waiter should be serving you. Yes, you're having meal. It's very common. Somebody comes and busses around, refills your liquids, and goes away. And so that's quite possible. Well, that's called efficiency, isn't it? So the poorest execution is when a waiter is stuck to a table, right? And cannot really go until the service is complete. That's not an efficient way to really run any business. Well, I'm going to come back to this code in a little bit, if you will. So we'll come back to that. I'm going to save it away as save. So we'll come back to that a little later and look at the same example a few minutes from now. But so we need to really rethink about the paradigm of programming. Well, now we talk about what are called subroutines. So what is a subroutine? A subroutine really is a function you call and you get back a response from the function. On the other hand, a coroutine, like the word co alludes to, it's a cooperating routines. So you can have two routines running at the same time and they can be talking to each other. This is like you and I are having a conversation. Maybe I run into you in the corridor and say, hey, how's it going? Of course, it's only polite for me to yield when I say, how's it going? Because I want you to respond back. And you say, oh, it's going great. It was raining heavily. And I'm going to say, oh, really? Did you bring an umbrella? So we are continuing a conversation here. And whatever you say and whatever I say, we build on that conversation, but we yield to each other. Well, that is like a coroutine. You got two functions continuing to converse with each other. So coroutines can be really nice to build up on a conversational state. And as a result, you can develop applications where you can do part of a processing and then come back and do more processing, if you will. But the question is, how do coroutines remember the data? If the threads could be switched around, how is it going to happen? This is where, what we have is a data structure called continuations. So what are continuations? Continuations are data structures that will remember the conversational state from one call to the next one. And continuations are amazing data structures because they will remember what you left with and they will come back and continue from there. So continuations are data structures useful to carry the conversational state between the coroutines. Let's think about this a little bit to understand what that really may mean. I'll give you a more familiar example just to think about it. Suppose I wrote a function, let's say a function right there, which takes an integer and returns an integer. And we'll call it as a create function, which takes a number as an argument. And I'm going to say over here, let's say we'll call this as an integer temp equal to n times 10, just as an example. But I return, let's say, an input, and I'm going to say input plus n, plus temp rather, is what I want to return from this call. Now, in this particular case, as you can see, we have a function that's coming in, and I can go back to this code and say, hey, I have a func given to me, which is coming from the create function. I'm going to send a 7 to this, and I'm going to output a func.apply, and I'm going to send, let's say, well, 7 times 10 is 70, and I'm going to add something to 70. Let's add a 5, and the result of this operation is going to be a 75. So that's not a very unusual code. Most of us are familiar with lambdas and how we deal with it right now. But if you look at this code, there's something very peculiar about this code, if you will, because we know this really isn't it. So just as an example, if you want to think about this particular code, I can put finally right here. And there's one thing you know about this code, isn't it? And that is, you can say temp is dead right now as you leave that block of code, isn't it? So when you run the code, temp is dead. And you are coming to the main function, and let's go ahead and say, let us call the func function. By the time you call the func, the temp is dead. Now you look at this and say, wait a minute, how in the world, if temp is dead, how in the world do I get this variable temp in here? How is it even possible? Is it magic, right? Well, it's not magic. It's called a closure, isn't it? So a closure is a lambda that captures the state, hopefully an immutable state, and you're able to carry it over. So in a way, logically speaking, a closure, if you will, is a really great data structure. A closure captures the lexical scope, and of course, and carries it over. So a closure is a nice way to carry particular state. So in other words, we can have data structures that move state around for us very nicely. So logically speaking, I don't want to simplify this overly to say this is what it is, but logically speaking, you could say, you can say continuations are like closures in that they can carry a state from one thread of execution, if you will. So they can carry the state from one thread, if you will, of execution to another. So that is really a nice data structure, which is called a continuation. So a continuation says, I will capture the data and carry it over to another state and have it loaded up for execution. This is kind of what you do, right? You're working at your office and it's time for you to go home. What do? You take some notes on your notepad or whatever, and you put it on your table, and then you leave. And when you come in the next morning, you look at the notes and say, oh yes, I remember I was working on this, and you get going. So we all leave the state for us to come back and resume. That's basically what the idea here is, that you have a state that you are leaving behind. But how does this really help to have this kind of a state in general? Well, the beauty of this particular state is that you can carry this across the invocations and can become really powerful. Well, you and I would probably never use continuation directly in code, but if you examine continuation in Java in Project Loom, that's a data structure that's available. And again, like I said, as an application programmer, I would not want to use it, but maybe a library or a framework writer may find use in it and they can look at it. But where does this really lead us into? What does continuation open the door for? Well, a continuation says you can park your state and come back and resume from it in another thread. So that leaves us wondering, how can I have such threads? This is basically what is called a virtual thread that you can create in Java. So what are virtual threads? Virtual threads are super lightweight threads. You say, wait a minute, why do they call it super lightweight? Because lightweight is taken already. So they have to use super lightweight. So threads are lightweight, virtual threads are super lightweight. Well, virtual threads don't occupy as much memory, and so you can create a lot of them. You may say, really? Lot like how many? Well, let's think about it. The virtual threads are actually managed by the JVM and not by the operating system. So in your operating system, in your JVM, you can create many virtual threads, and the virtual threads have the feature that they don't get blocked and wait when your tasks wait. So logically, I would say, think of a virtual thread like waiters in a restaurant. So when you are blocked, I'm wondering what I want to order for a drink. You cannot proceed without you order the drink, but the waiter doesn't have to block and wait. They could go bust around other tables and come back and say, have you decided? And you can continue. So think about it this way. When a task says, I want some I/O to be performed, I want to do some operation that doesn't really require the CPU, the task is going to get blocked, but the thread goes away and does other work. When the task is ready, imagine this like you were Windows programming or you were swing programming. What do you normally do? When your button click happens, you don't immediately do the work. The button click simply puts an event in the event queue. And then on idle, something picks up that and executes it. Think of that logically the same way. When your task is saying, I'm running. Oh, wait, I got to wait for something. The thread says, why don't you wait? I'll be right back, and goes away. When the task is ready to run, internally an event goes into the event queue, and a thread can pick up and execute that because it's ready. So this becomes really a nice way for us to be able to execute code. Let's examine this and see how this actually works. So when a virtual thread blocks, the task is going to wait, but not the underlying thread, and it can continue executing. Let's think about the problem we saw about the limitations on the thread and see how we can handle that. So remember, I saved this code away a few minutes ago. So let's go ahead and take a look at the code we saved. So remember, we had no problem with 1,000 threads earlier. We were able to create 1,000 threads, not a problem at all. On the other hand, unfortunately, what we saw was I was not able to create 10,000 threads. Somewhere between 5,000 and 10,000, it failed. You saw this earlier. But the question is, what can we do to improve this? So that's the question we want to answer right here. So I go back to the same code we saw here, no difference, except one thing I'm going to do here, if you don't mind. I'm going to just make it wait a little longer just to be sure. So I'm going to say over here, let's say a thread.sleep. I'll make the main thread itself wait a little longer here. That doesn't change in it. Actually, I'll put a little, maybe a 6 seconds delay here just to wait for it. And then we will continue right after that. And just to illustrate the point, that didn't change anything in our code. If it's going to run into a memory problem, it's going to run into a memory problem. No difference, right? Now, let's go back to this code right now and say, hey, I want to start the thread, but I'm going to say a thread.start virtual thread. By the way, this is part of Project Loom. And of course, it's in pre-release right now. It's not really something you can use readily. And if you install the version of Java with Project Loom in it, you can try this example, but not in the Java 18 or earlier. So I started a virtual thread right there, right now, as you can see right there. And I'm going to go back to this code and say, create me a modest 10 threads right now, like we did before, as we did a few minutes ago, right? So that's basically what I'm going to do, a start virtual thread, and I'm going to provide the symbol for it right in here. Let's try to make sure that is correct. So thread start, a virtual thread. It does require you to spell it properly, which is kind of unfair, but so virtual thread. Okay, so basically, I'm waiting for the day when the compiler knows what I mean and not what I type, right? This is too unfair. Anyways, so right there, I'm going to run the virtual thread. Let's see what it's going to do. Ooh, a null pointer exception. That's not good. So I'm going to go ahead and start the thread because I don't have a thread to join. I'll simply say set that to the thread so we can actually use that right there. So that's my modest 10 threads I started right there, and it says I'm going to run that and produce the output. It's going to say done at the end of that time duration, isn't it? When it's actually done, it should tell us it's done, so you can see that it's over. Well, great. But I'm going to go ahead and move this a little bit here and go back to this and say, hey, give me about 1,000 threads for me right now. And we can see what's going to do when I do 1,000 threads. It started. It doesn't have any problem starting it. As you can see, that's going to run. Hey, what if I say 10,000 threads right now? And you can see when I started 10,000 threads, which failed, remember, for the normal threads, and the 10,000 threads are running just fine, as you can see. What if I said 50,000 threads right now? And you can see that in this particular case, that starts up, not a problem at all. What if I say 100? I feel like I'm doing an auction here, isn't it? What if I do 100,000 threads right now? And you can see that it's like I can handle 100,000 threads, not a problem. And now, of course, I say, why stop there? Why don't you give me 1,000,000 threads at this point? And if you're like me, you don't know where the zeros end, so I'll put a little underscore right there. That's 1,000,000 threads that we are asking it to build. And what does this say? It says, why don't you give me something more challenging, right? So essentially, we were able to create 1,000,000 threads right here, and it's like, I can handle this. So what's going on right here, if you think about it? It's not the fact that I can create 1,000,000 threads that excites me. What excites me is that the sleep function is not holding the thread hostage. So it's saying, look, I want the task to sleep. Why in the world would you wait around when I'm sleeping, right? Why don't you go do other things? When I'm awake, you can come back and process the information. So this is where you're getting the benefit of this, if you will. So here is another way to really think about what this is going to do for us. Well, first of all, you don't need to be worried about creating more threads on your system because the constraints are no longer the same. You are able to create more threads if you really wanted to. So where does this really take us in this particular case? Well, first of all, when you perform an I/O, you don't have to block and wait. So here is something I want to quickly show you just to exercise this to understand how this works. So if I go to the do work function, just to illustrate this, I'm going to say over here, let's say index right there, and I'm going to output right here, let's say index plus, and I want to output a thread dot, let's say a thread dot current thread, and I want to display the thread information right there, and then I want to print it again afterwards right there, after a 5-second delay. So I'm printing the index on the thread information for you a couple of times. Let's go back to, again, a modest value of 10 right there, and we got the thread coming in. We will ask it to use a regular thread like so, and we will execute that code, and we'll print that when we are done with it. So in this particular case, we are simply printing the values, as you can see, but what are we going to send to this particular function? Well, in this case, I'm going to say index, and I'll call the do work and pass the index to it right there, and we'll say index equal to I and pass that value in here. So when you run the code, what are we expecting to see as an output in this particular case? So obviously in here, we got an index value coming in, and the thread constructor is going to call the do work function. The do work function says, I'm going to take index as a value. I'm going to print it out right there. Let's go back to the thread itself and see what the thread wants to do. The thread is going to simply pass that function as a runnable and be able to execute it. Let's see what I'm doing wrong here. So it says thread runnable is not applicable. It's not happy with me. No suitable constructor found. That's a lie. Let's take a look at what it's doing right here. Oh, of course, pardon me. I'm sleeping at the wheel, right? It's runnable. So let's go back and run that. And we will say in here, we're calling it. I want you to take a note of this output right here for a minute. They made this too easy in this case, right? So notice what these numbers tell you. Thread 0 executed 0, and thread 7 executed 7. thread 1 executed 1, it was in that order. And if you look at who finished it, thread 0 finished 0, thread 3 finished 3, thread 7 finished 7. So what does that kind of alludes to? Looks like those threads were kind of hanging and waiting, and the task is sleeping, and the threads are having a great time partying, right? And saying, hey, we don't have any work to do because the task is sleeping, but why? So here's a way to think about it. Going back to this code, let's go back and use a regular, a virtual thread instead. And so in this case, I'm going to say, go ahead and call the doWork method. And in this case, pass the index over to that method and see what it's going to do. So now notice what's happening in here. You have a task 0, and 0 was executed by worker 1. Let's look at 0. That's a worker 9. And you can see that in this case, 1 is worker 2. On the other hand, 1 here is worker 10. And you can see 3 is worker 4, and 3 is worker 5. You can see that the context switching happening right there between the threads. So the sleep did not actually have to sleep and wait and use the thread. The thread said, well, you're at sleep, I can do something else. So as a result, it's a lot politer in terms of how you can execute it and doesn't have to waste your resources. So this can be really helpful for us to be able to scale really well. So how would this really benefit what we want to do? Well, yes, please. Right, so we didn't do anything useful because our thread was just sleeping at this point. But in this case, I did ask it to start those threads personally myself, right? So, but they are virtual, so they're not occupying the underlying thread. So they can be in a pool to switch around. So if you were to assign a pool of threads, then the pool of threads is going to be serving your task. This was a contrived example because I literally asked it to start that many threads. But typically, you're going to create a pool and schedule tasks on the pool, right? So which means you can schedule more tasks on the pool. And if those tasks are going to block on the I/O, you don't need more threads to serve it. Yeah, you're going to reuse the thread because they are doing nothing and they can be reused essentially, right? And of course, starting threads in a loop like this is naive, but it serves as a simple example to illustrate the point. But what we can do, though, is we can take this idea and say, hey, why don't we really get moving a little further in how does this really help us? Well, where this really helps us is we can perform I/O tasks in a non-blocking manner. And you may say, if I can perform tasks in a non-blocking manner, how does it really help us? Yes, it helps us in better use of threading, but is that all the benefit is? Well, as it turns out, there is yet another benefit we want to think about. And that is when you make an asynchronous call, it is not always the happy path you are interested in. What happens typically is when your call fails, you want to do exception handling. And when you have to do exception handling, what happens when you are asynchronous? Well, if you're going to get a call back later on, your callback will have to handle the exception and decide what else to do. The code becomes really clumsy. On the other hand, if you're using something like completable future, well, the nice thing about completable future is the code is functional style. But unfortunately, that also becomes really hard to handle exceptions. There is no good answer. Well, there's one place where we are really good in handling exceptions, and that is in imperative style code. Now, the beauty of this approach is you can write code in imperative style and you can handle exceptions in an asynchronous manner really well. Let's see how that's actually going to be possible in here. So let's say for a minute, I want to write a function here, and the function is, we'll call it as a getLength, let's say, where the getLength function takes, let's say, a string. Let's call this as a string file name, let's say. Well, I'm going to pass a file name right there, and I put a try block. And within this, I'm going to say a catch exception, an I/O exception, as you would expect. And in this case, I'm going to handle the exception somehow. We'll think about this in a minute. So I'm going to say here comes an I/O, but I'm also going to bring in an NIO.file in here as well. So I can say here, return files.lines dot, let's say a paths.get and the file name, and then I can say on this account, get the number of lines in this case. But what if that were to fail? Well, you can say here, handle the exception and make a call to another service, if you will, right? So it's possible, call another service, etc. We can do whatever you want to do based on your problem. You could do that in here. So the beauty of this approach is this is going to come in and do the work when the exception were to happen. But on the other hand, if I were to go back to this code right here, and I'm going to call that particular function like so I can say right now, use the getLength function I want to call. So I can say right here, a thread, let's say a thread dot start virtual, let's say virtual thread. And the thread I want to start here is to say, call the function getLength, if you will. And when you call let's actually call a function called, a call. And the call function is going to do the actual work for me. But what am I going to do in the call function? In the call function, I can say, hey, I want to go ahead and call this function output, let's say, getLength for the sample, let's say, sample.java file that I have with me right in here. So I'm going to make a call to that sample and print the result of that particular call. Let's do this really sequentially for now. And then we will worry about the multithreading or asynchrony after that. A synchronous call, so simply call the call function. So what does the call function really do for us? It's going to print the results for us in the very end of this. So java.io and java.nio, those are the two things I want to bring in right there and use them. So very simple code at this point. So what is the file name right here? The file name, let's change the case right there. There we go. So that's the file name we pass in, and we get the data out of it. All right, it's picky, it's a long. Okay, fine, I'll help you with that. So let's go back and say that's a long as well. Are you happy now? Okay, so we're going to ask for that particular information. Return a 0 for now. We'll get back to that. So essentially, this is going to give us the result of a 22. But what happens if I want to run this in an asynchronous manner? Well, you can say a thread.start a virtual thread. And in this case, I can simply say, do the call to the call method, right, like so, and I can run that in a virtual thread, isn't it? And in this case, I'm going to just delay it a little bit so we can actually see the result and wait for it. Just to illustrate the point, how does the execution actually work? So if I were to run this code right here, it says 24 as an output. But what did we gain by doing this? Well, first of all, if you were to observe the thread of execution right there, you can say what thread is executing this particular code. So you can say enter, and in this case, I'm going to say a thread, let's say a thread dot virtual thread, and again, thread dot current thread. Again, I want to emphasize, this may not show you the actual result in here because I only have one thread created. But in the previous example, you saw how we saw the context switching, and think about it in this particular case. So we'll say exit. So we are entering and exiting at this particular point, and you can see that it's a thread that's entering and a thread that's exiting. But imagine running this in multiple threads, if you will. What you're going to then see is this call may happen in one thread, but because that's going to take some time, if an exception happens, another thread may handle the exception. And this may be handled by another thread asynchronously, so you don't have to wait on that call to do this operation or this operation. And besides, when you come into this, you can make a call to yet another service, and that becomes asynchronous. So as a result, the benefit you gain from this is your code can be asynchronous, but you can also handle exceptions really easily as well. And if you really think about where we are today, from the time we started programming in Java about 25 plus years ago, well, we are living in the world of microservices. We are living in the world of serverless computing. We are living in the world of microkernels. We want to be doing more asynchronous calls to other services. And so the world is moving towards this kind of network-based communication more and more. And this really draws the line to make it much more simpler and easier. So better utilization of the resources, but also a better and easier way to program as well. And that's basically where the net benefit is in terms of where we are going with this. And that's basically what you can see in the case of Project Loom when it becomes available for us to use. So, but where does it really make sense to use it? One thing to keep in mind is this really is useful in the case of applications that do a lot of I/O. Computationally intensive threads won't benefit a whole lot from this, because this is really useful when you do this context switching. If you're going to be busy processing, there's not a whole lot of benefit. But a lot of what we do is communication, network communication. So this model is something that will really benefit. And that's kind of where we are going with Project Loom. That's all I have. Hope that was useful. Thank you.